comes Tristan Dupuis on the inside. Tristan Dupuis to third, now all the way up to second. Tristan Dupuis out of turn number 4 to the checkered flag. Tristan Dupuis, the veteran limited late model driver, in victory lane again here at Flat Rock. Ladies and gentlemen, here's your host for today's presentation, Tristan Dupuis.
Hello everybody. We're at the Jack Sports Race Car Shop in Lansing, Michigan today, where we're covering chassis setup for Dwarf cars and Legends cars. Some of the topics we're going to be covering today will be, first and foremost, safety, handling characteristics, front end geometry, rear end geometry, wheels and tires. Also, we're going to have a section on springs and shocks, as well as weight and balance. We'll show you how to scale your Dwarf car or Legends car. And in conclusion, we'll have details on what to do at the racetrack when you incur handling problems such as oversteer and understeer, and detail how to solve those problems. As many of you may already know, chassis setup is the key to winning in any type of oval track racing, especially in Dwarf cars. Viewing and understanding this video will not only improve your racing, but it will enable you to win. Okay, in this section we're going to be talking about safety. Safety is one of the most important things about your Dwarf car. Safety is often overlooked and often isn't even focused on until after the event of an accident. So we're going to try to take a real close look into safety first. A lot of tracks have minimum requirements that you have to meet. Today I'm going to show you everything that we feel is necessary in order to be safe in the Dwarf car. We're going to start out with the helmet. There's several different types of helmets that you can buy, open face and full face helmets. If you go with the open face helmet, the benefit is that they have very good visibility. The disadvantage is that they have poor protection for your chin and the front of your face in the event that you really get in a bad accident. I do like the full face helmet, but you have to make sure that you have one or buy one that has good visibility on the peripheral, where they have it actually cut away like this. This is a Simpson made for racing helmet, and it does provide very good visibility. All your helmets should be fairly new, and you should check the tags, make sure they're up to date and meet the current Snell requirements. The next item we have is a fire suit. Fire suit's a very important item. One of the biggest dangers in auto racing is fire. Here I have a Simpson one-piece, two-layer suit. Fire suits do come in 1 and 2 piece, also single and multi-layers. You want to get yourself a real good fire suit. It's worth the extra money. Remember the old adage, hindsight is 20/20. Get yourself a good fire suit. The next item we have are racing gloves, which are fireproof gloves. These particular ones are made by Simpson. They're fairly inexpensive, fairly high quality. They're definitely worth the money. Fire gloves are definitely something you need to have. In the event of fire, you need to be able to have your hands cool enough or not burning so that you can undo your belt to get out of the car. Simpson fire gloves. The next item we have is, we call it a horse collar. It's actually a Simpson racing neck collar. It goes around your neck. It has a Velcro attachment. And what that does is it helps alleviate whiplash or sudden jarring of the head in the event of a collision. This again is also a low dollar item. I'm going to say around $30 range, and it's a really good item to have. Could save you a neck injury. Next item we have are Simpson 3-inch wide racing belts. Almost a mandatory thing for racing. Belts are available in 2-inch. We definitely recommend the 3-inch. They give you a lot better support, and they also distribute the load more evenly on your body in the event of collision and make the chance of injury a little less likely. One of the things you need to watch on the belts is there's a SFI tag that has a date. Most belts do have a certain time period, usually like 2 years, where they're still considered being good. You need to make sure your belts are up to date. Buy 3-inch wide belts. The next item we have here is going to be aluminum racing seat. The seat again is a very, very important safety item. There are fiberglass seats on the market and they're a very bad idea. We like the full shell aluminum seat that has the wraparound sides. It gives you much better protection of the torso in case of a real harsh collision. You should follow the manufacturer's instructions for mounting the seats, as you should the seat belts as well. When you buy these items, they do come with mounting instructions, and you need to pay particular attention to those instructions. The mounting of the seat is very, very important. One of the other items, as we talked earlier about fire, a very, very important item. When you get in a collision with a Dwarf car, because of the nature of the Dwarf cars being so small, it's very important to be able to get out of the car, but a lot of times you can't get out quick enough, and in the case of fire, you need to be able to suppress the fire before you can get out. What we recommend is gas bottle. It's a fire suppression system. In our race cars, we usually use the Phoenix brand fire suppression system. There are other brands on the market. This system is plumbed throughout the cockpit. It's real easy to install, and at the push of a button, it will extinguish all the flames in the cockpit and buy you some time to get out of the car safely. Again, fire is probably the biggest danger in circle track racing, or at least I believe it is, in terms of being life-threatening. These are all really good items, and you shouldn't cut corners when it comes to safety. Now let's take a look at the structural part of the car and discuss safety there. Here we have a Dwarf car under construction. As you can see, this one features integrated door bars, which is really a good safety item. A lot of cars on the market, a lot of cars that are out there racing, don't have integrated door bars. The doors are hinged. For Dwarf cars, it's really not a good idea. I believe the Legends may mandate hinged doors, or at least hinged door bars with the door. This is a lot better setup. It's a lot more rigid and a lot safer. This particular frame was computer designed for both rigidity and safety. The driver's side has the top door bar is hinged for easy access. The remainder of the door bars are also integrated. This car features an X in the floor, which is really a good idea to have. We have inadvertently crash tested some of these cars, and that X shape in the floor, the X bars, do keep the car from getting diamond shaped, the frame from getting diamond shaped. It really does protect the driver because it keeps the cockpit from deforming. As I said earlier, there's a lot of lesser frames on the market. If you already have a car, you might be committed, but if you're purchasing a car, you need to look for a car that has a really good frame, a really good structure to begin with. In the interior portion here of the cockpit, this would be where the fire system will be going. The fire system is plumbed throughout the car. On our particular cars, they're plumbed in the engine compartment and the trunk as well as the cockpit. That'll extinguish any fires that could arise, whether they start in the trunk or under the engine. One of the most important items in terms of safety and the construction of the car is the brakes. Make sure your car has very good working brakes and as big a brakes as possible. We have had situations, I have personally had a situation where the throttle stuck, and had we not had extra large brakes on the car, we would have been in a world of trouble. Brakes are very important. You need to keep them balanced, and you also need to keep on top of them maintenance-wise by bleeding the brakes and doing just regular maintenance. Brakes need to be in good working order all the time. I'd like to take just a few minutes and talk about handling characteristics. Basically, there's three modes of handling characteristics: understeer, oversteer, and neutral steer. We'll address them one at a time. First one is understeer. I would define understeering by saying understeering is the condition where you have the wheels turned on the car. In racing, it would be the wheels turned to the left, but the car has the tendency to still go straight. There are some slang terms that are synonymous with understeer, such as pushing. That's a real common one in racing. People say, my car is pushing. And what it means is the wheels are turned, but the car is still somewhat going straight, or the car is not turning to the same degree that the tires are turned. The next term we need to clarify is oversteer. Oversteer is the condition where the tires would actually be turned to the right, but the car going to the left. Some slang terms for that would be loose would be the biggest one in racing. A lot of people say their car is loose. And what that actually means is it's tail out, the wheels are turned to the right, and the car is turning to the left. Both of those modes of handling are undesirable. It's really important to keep a good handle on your chassis, to keep the chassis set up. You need to know what your car is doing and where it's doing it on the track. So you need to get a good feel for what understeer feels like and what oversteer feels like. Sometimes people take a white piece of tape and put it on the steering wheel, and that way when they're racing they can actually see if the tape is turned way around, in other words the wheel's turned way to the right but the car is still going somewhat straight, they know their car is understeering. Consequently, if the wheel is turned all the way to the right or far to the right and the car is still going to the left, then they know their car is oversteering. When you're a beginner racer, sometimes it's very difficult to distinguish between the two, so you need to take a lot of time and effort to be able to do that. Sometimes observers from the grandstand can give you a little bit of insight on what they see, because as a car travels around a track, if the car is extremely understeering or oversteering, the observer can see it. The third mode that we didn't talk about yet is called neutral steer. That's my favorite. That's where the car handles good through the corner. You turn the wheel, the car turns commensurately with how much you have the tires turned. The back end is not sliding out in a loose condition. It's neutral. Sometimes people, if they get their car real neutral around the whole track, they'll use the term, my car was on a string. And that's what that means. Neutral steer is what we're trying to obtain. Front end geometry is a very important part of the race car. In order for the car to go around the corner, the car has to turn. If the front end geometry is correct, the car will turn good and eventually you'll be able to win races. One of the main topics in front end geometry is going to be ride height. Now, a lot of manufacturers spell out what the ride height is for their car. Let me just explain for a minute what ride height is. If this is the ground line, and this would be the wheels of the car, the frame would be here. What they refer to as ride height, it could be measured in different areas. Generally we measure it in 4 corners on each side of the car, here, here, and of course on the other side of the car. That distance right there is what the ride height is. The ride height of the front of the car is really independent of the ride height of the back of the car. Some racers believe that the car has to be at an even ride height all around, such as maybe 4 inches all around the car. That's really not true. The rear is independent of the front. So what determines the ride height in general is the front end geometry. What I like to do in order to determine ride height is to get the angles on the lower control arms to where I want them. This is a front end view of the basic suspension components in the average dwarf car. These, of course, being tires, these being lower control arms, spindles, upper control arms. In order to find out which ride height is best for you, in general, what I do is measure this distance to the ground, which would be the inner pivot point of the lower control arm, and the center of the lower ball joint to the ground. These arms should be somewhat flat. So the dimensions should be the same, plus or minus, I'm going to say, about 1/2 of an inch. In other words, this point can be up to 1 inch lower than this one, or this one 1 inch lower than that one. But no more than that. That would be the limit. And the car should be reasonably flat. It is okay to run the car up to maybe 1/2 inch lower on the left side. But that's one of the main constraints that will dictate the front ride height. One of the issues we need to talk about when discussing front end geometry is a term called camber change or camber gain. And what that exactly is as the body rolls in the car, as you go in the corner and let's say the right front corner goes down, that would mean these 2 points here, which connect to the frame, would go down in this direction. When they go down in that direction, this arm swings an arc. At the same time, this arm swings an arc. Being that this arm is shorter, it swings a sharper arc. And what ends up happening is it brings the upper ball joint in relative to the bottom. So analytically, if you went into the corner and my hand represents the tire, as the body rolls, the tire actually goes in like that. You actually increase in camber on the right front as you go into the corner and the body rolls. Consequently, the same thing happens on the left front, only it's to your advantage as well. This is a longer arc than this, and as you transfer weight to the right, and this corner of the car actually comes up as the body rolls, these 2 points go up, so these arcs swing. This arc straightens out, this arm straightens out, and because the arc is steeper, it actually makes the top of this tire go out. So again, as you roll into the corner, if my left hand indicates the left front wheel, as you roll into the corner, this tire actually goes like this, which is to your advantage. And the reason being, as you turn the corner and the lateral acceleration, or the amount that you're turning, increases, the tires deflect. And if you can have the tires so that when you're in the middle of the corner, so that they're over like this, they're deflected at the bottom, and they end up, the contact patch of the tire actually ends up being flat, which is beneficial. Well, you might ask, how do we get all these angles and everything? And there's a couple different ways to do it. One is you can buy a computer program and you can get very deep into the numbers, and it's somewhat difficult to understand. Or I can give you just a relative setup of where to be, relative numbers as far as the angles go. And again, we call this camber change. When the body rolls and the tires move in the lateral direction, that's referred to as camber gain. Usually we associate camber gain with having a high roll center. We've all heard that term. Not a whole lot of us know what it is. I'm going to try to explain the front roll center and how it relates to the camber change. In general, I'll just state this, that number one, the higher the roll center, the greater the amount of camber gain. And number two, the lower the roll center, the less camber gain. Okay? Before we get into the roll center, I will say that in general, roll centers towards the lower side, which I'm going to say around 2 inches, are beneficial. And also, camber change, having it to a greater side, is beneficial. So because they conflict with each other, there has to be an even trade-off. There is an optimum trade-off between roll center height and camber change curve. Right now I'm going to show you analytically how to find the roll center of your front end. And we'll do this initially by drawing the front end view just as I have. These lines indicate upper control arm, lower control arm respectively. Upper control arm, lower control arm. And how we find the roll center is initially we take and we draw a line, we extend the line that represents the lower control arm. Let's do this side first. If we extend this line, I'll just make a little dotted line here. And then we'll extend this line as well. We extend these two lines. We end up with a point of intersection, which would be right here. Now, if we take that point of intersection, which is called the instant center, at any given moment when that tire is traveling up and down, this point right here is the instant center of these two links. Now, once you find the instant center, which we'll label IC, what you do is you draw a line back to the center of the contact patch of the tire, which would be right here. So we'll draw that line back. Just like that. Okay. Now, this line right here, we'll do the same on the other side, and where this line intersects the line from the other side, that will be the true roll center of the car. So again, we're going to go through this whole process that I just did, finding the instant center and then drawing it back to the contact patch. We'll be doing it for the other side. And again, we'll start out by extending this line. And then we'll extend the line through the upper control arm. And they intersect right here, or somewhere near. And now what I'll do is I'll draw a line back to the center of the contact patch, which would be approximately there. Now the point of intersection of those two lines that I just drew is exactly right here. And the distance from the ground line to that point of intersection is the roll center height. And right here it looks like it's approximately 2 3/4 inches. You also notice that if the center line of the car, which would be right about here, it's offset from the center line of the car a little bit to the left. That's pretty common. Roll centers very seldom lie on the center line of the car. They are usually offset, and I would say most of the time they are offset to the left. So this all worked out actually better than I thought it would. That's how you go through finding the roll center. Again, the lower the roll center, the better the car seems to turn on long runs. For example, in a 50-lap race, a low roll center is beneficial. For qualifying, a high roll center is beneficial. The unfortunate thing is it's very difficult to change the roll center height because you get into like changing spindles, changing mounting points of control arms, and it's somewhat difficult. So it's not something that you do at the track. You originally find out where the roll center is over the winter time, for example, change it if you can, and then the rest of the year you pretty much live with it. The roll center is not a tuning aid. It's not something that you do at the racetrack. But this is a procedure you would use to find the roll center. I'm going to give you some approximate angles so that you have some ballpark idea where to set your car up and where the ride height would be. Again, always look at these lower control arms, and you want to strive for them being flat, and the dimension I'm going to give you is plus or minus 5 degrees. If they're within 5 degrees either way, either uphill or downhill, that's acceptable. I'd rather have them 5 degrees uphill than 5 degrees downhill. The reason being, if they're 5 degrees uphill, it means that you have the ride height as low as could possibly be. On the upper angle, I would say the range there would be probably from 12 to 22 degrees. 15 degrees, 15 to 20 is probably optimum. If you get those arms somewhere near those angles, you should be in good shape. Just to reiterate our demonstration on front-end geometry, we're here at the Dwarf car that's under construction, and we're going to illustrate the angles of the control arms and ride heights. First off, we'll show you where we would set the ride height, or what would determine the ride height, and it would be determined by this lower control arm. We would set the ride height measuring from the ground to the frame rail so that this lower control arm was at plus or minus 5 degrees. I'm going to put it at 5 degrees uphill to the outside. That's 5 degrees uphill to the outside. That's the maximum. Ideally, you'll want it flat at 0 degrees. Okay? If you have to, for some reason, you could run it as low as 5 degrees downhill like this. And again, we're talking about the lower control arm angle. Preferred is 0 degrees. You could run it as much as 5 degrees uphill. And we'll just take a moment and measure the angle of the upper control arm. At 5 degrees uphill, the upper control arm is at a maximum of 22 degrees. And let's just see what it falls to at 0. At 0 on the lower control arm, the upper control arm ends up at about 15 degrees. So those are basic guidelines on finding the ride height. Now the camber change curve that we talked about, I believe we can illustrate that just by traveling this suspension. And what we'll do here, we'll put the angle finder on here. I can't really see what it is, but as I'm going to travel up, and this will simulate rolling into a corner where the front end corner of the car would go down, the tire would go up like this. And you can see as it goes up that the camber increases. The tire goes from being like this to being like this as I travel up. And of course the opposite on the way down. Now if you want to gauge your camber gain, what you can do is use a tape measure or a toe gauge and actually measure it like every inch. And what you're looking for is about a degree to a degree and a half of increase in camber, increase in negative camber, which would be in at the top, per inch of suspension travel. So in other words, for every inch you go vertically, this rotor or wheel assembly should increase in negative camber 1 to 1.5 degrees. If you're in that range, you're in pretty good shape. This section deals with front end alignment. In general, there's only 3 components to front end alignment, they being caster, camber, and toe. First, let's look at caster. What caster is on an automobile is the difference between the angle that the ball joint center line lays on versus the vertical angle. And let me explain just a moment. I've drawn this solid white line with the level. That is a vertical line. It is truly vertical. Here what we have is a tire with a spindle assembly, this being the spindle right here. Upper ball joint center, lower ball joint center. And what I did was I drew a dotted line intersecting those 2 points. Kind of a little sloppy, but okay. And as you can see, that angle of the ball joints is different than that of the vertical line. Now, this being the left front tire, front being this way, it means that the line drawn between the 2 ball joints is tilted towards the back of the car like this. We refer to that as positive caster. If it was the other way around, where the upper ball joint was ahead and the lower ball joint was back and the dotted line was at an angle like this, that would be referred to as negative caster. In general, just to give you a guideline, on our cars, on our Dwarf cars, we do run a little bit of split in the caster, meaning we run a little bit more caster on the right front than on the left front. It helps pull the car to the left into the corner and also reduces steering effort a little bit. In general, what I'd recommend for a range would be for the left front to be anywhere from 1.5 degrees positive all the way to 4 degrees positive. And that means that if you put either a caster camber gauge or an angle finder or anything along that line, along that dotted line, it should read on the left front between 1.5 and 4 degrees. My personal preference is I like a lot of caster. I like to run it at 4 degrees positive on the left front. So this line right here would be 4 degrees positive, meaning that the upper ball joint would be back farther than the lower one. Consequently, on the right front of the car, we run a little bit more caster, and as I said, that helps pull the car to the left into the corner. The range there, I like to run between 4 degrees positive all the way to 6 degrees positive. And that range right there gives you enough caster split to where the car has a good feel pulling into the corner. Positive caster, the higher end number you get positive, in other words, the more positive you get, if you get up into numbers like 4 and 6, it does increase the steering effort a little bit, but the advantage is it increases the feel of the car, and it has other geometric effects. Positive caster is, to me, it's nothing but a good thing, provided you can still steer the car. Don't go so high on caster that you have a problem turning the car or end up getting tired even in a short race. But run as much positive caster as you can on both sides within these limits. Just a quick illustration on caster. I've put the angle finder parallel to the spindle. This car, of course, is the one that's under construction. This doesn't have a strut rod on it, so it'll be real easy to show you. If I move the lower ball joint ahead or move the upper ball joint back, you can see that would be positive caster. In fact, that's quite a bit positive. That's 10 degrees positive. And if I move it back this way, that's about 10 degrees negative caster. There's basically, most dwarf cars, there's two ways to adjust the caster. One is if you have an adjustable upper control arm, which this one is, you can thread the Heims joints to bring this upper ball joint either ahead or back as you desire. Or on this car, which has a strut rod that runs to the lower control arm, by twisting that or threading that, you can bring the lower ball joint ahead or back. Now, before you really get in depth setting the caster, there is one measurement that you should make, and you need to have a reference in the frame. If your car's never been crashed and the frame is nice and square, I usually find one of the cross members in the car, a member that's square in the car and goes across. What I like to do is string a line parallel to that member, and then what I do is take a tape measure and measure from that string to the center of the ball joint on each side and make sure that that's the same distance. So what we would do is hang a couple of jack stands and run a string parallel to the cross member line of the car. Then measure directly ahead from that string to the lower ball joint on each side and make sure that that distance is the same. If that distance is the same, you know that the front of your car is good and square, and then you can adjust the caster accordingly. We'll take just a minute or two here and talk about camber. Camber in the car is pretty much the angle that the tires are on. If the car was viewed from the front, the amount that the top of the tire is tilted towards the infield of the racetrack is the amount of camber. In general, there's two ways to check the camber. One is to use a commercial caster camber gauge, which you would use and just follow the instructions. Or you can do it the cheap way, the way we do it, and that is with just a regular $15 angle finder. Now, first off, you need to find a good surface to put the angle finder on. If your wheels are nice and straight and true wheels, you can actually set it right against the rim like that. And the amount of camber would be the amount that this wheel is tilted towards me or away from me. If it's tilted towards me, it's positive camber. Now, the left front of the car, you want positive camber. The range that you want is anywhere from 1 3/4 degrees to 2.5 degrees. So the top of this tire tilted towards me anywhere from 1 3/4 to 2.5. This one falls right at 2 degrees exactly. Now if we go to the right front, it'll be the same thing, only the camber on the right front will be negative. Being that the top is tilted towards me, it'll be negative camber. On the right front, the range would be anywhere from 2 to 3 degrees negative camber. So if my hands illustrated the front of the car, my right hand being the right front, my left hand being the left front, you would want both tires like this. The right front being 2 to 3 degrees, the left front being 1 3/4 to 2.5 degrees. Positive on the left front, negative on the right front. If you have a caster camber gauge, follow the manufacturer's instructions and they'll show you in detail how to check the camber. The last aspect of our front end alignment is toe-in. A toe-in would be how much the front tires are pointed towards the inside or towards the outside. In other words, if my right hand was a right front tire and my left hand a left front tire, toe-in would be how much in or how much out the tires are facing. Let's give a little illustration. Before we get into setting the toe, there's a couple of things we need to talk about. One is, before you do any alignment work, being caster, camber, or toe, You need to set the ride heights on the car, like we talked about a little bit earlier, and also set the tire pressures so that the car is in the same condition it would be raced in. It's not a bad idea to have the driver in the car as well, or have weight to simulate the driver, as well as things like fuel load. When you do the front end alignment, you need to take all those things into consideration. It has to be pretty much the way it would be when it's going out to race. Again, before we do the toe, we make sure we have the caster and the camber complete. And the procedure you'd follow for doing the toe would be, number one, you would make sure that the rack, the steering rack, if your car is so equipped, is in the center. If you have some other form of steering, you need to make sure that the mechanism between the wheel and the tie rods is in its center position. And this car is pretty easy. I can just glance down and see that the tie rod ends are lined up with the lower control arm inner pivot bolt on each side. Now I know that the rack is centered. Secondly, if you just assembled your car and it could be way off in tow, what I like to do is get down and sight down the plane of the tire. Look right down the outside of the tire in line and line it up with the back tire. That'll tell you if the tire is grossly pointed in or out. And what you can do is loosen your tie rod adjuster sleeve and adjust it by eye before you ever even start doing the measurement. Give it a quick toe adjustment by eye. Every time you do adjust the toe, make sure you give the car a little bit of a bounce to settle it out, and just roll it back half a turn or so, half a turn of the wheel and back. And what that does is takes any residual stresses out of the tires and just makes the alignment more true. After you've centered the rack and sighted the tires and gave the tie rods the gross adjustment to get it in the ballpark, then it's time to put the measuring stick on and see where you're at. Most of our cars we run in the range of anywhere from straight up for toe in to 1/4 of an inch in the outward position. So anywhere from 1/4 to 0. And how we check it, we use a toe stick, which is something you could even make at home. It's nothing more than a piece of 1-inch square tubing shaped like this, like a clamp, and this side slides. It has a pinch bolt to lock it into position. Now, if Ken would be kind enough to come in and give me a hand, we're going to check the toe on this car real quickly. Ken holds the end of the toe gauge up against the tire, doesn't press hard, not hard enough to deflect the tire, and then I slide the sleeve until it just touches the tire in the front. And as it just touches, I'll tighten up the sleeve a little bit to snug it up. And then I'll wave it back and forth here just to make sure that it's a nice tight tolerance. Okay. As we check it here, I've got about an 1/8 inch gap, which would indicate that the toe in is 1/8 inch out, which is exactly in the middle of our range, which was 0 to 1/4 inch out. Had the toe been out substantially, either out or in, what we would have done is sighted down the plane of the tire and find out which tire was in or out and adjust that one accordingly. Each time you do make an adjustment on the car, you need to bounce the car real quick and roll it back to center everything out, and then follow the procedure exactly again. Put the toe stick in the front on the high spot of the tire and check that, and then check the back until that gap that you have in the back is what you're looking for. Again, the toe gauge should go just touching both tires in front and then move it to the back, and the gap that you have in back is representative of how much toe out you want. We usually don't recommend running the cars towed in. And there's one other issue we didn't touch on. This is assuming that you have fairly straight wheels. If for some reason you're in a bind and your wheels aren't straight, what I like to do is jack the car up and put a screwdriver on an oil can or something near the tire and spin the tire and see how much run out it has. If it has an excessive amount of run out, take either the lowest spot or the highest spot and put it to the bottom. What that'll do is it'll give you a more even wheel on the sides, and it'll give you a better approximation of your toe. So even if your wheels are bent a little bit, if you put either the highest spot or the lowest spot towards the bottom, you'll still be able to check your toe. Another aspect under front end geometry is the concept of sprung and unsprung weight. Let me give just a little explanation. If you were in a real smooth riding car like, let's say, a Lincoln Continental, something that that you don't feel a bump on at all. When that car hits the railroad tracks, everything that does move on the car is unsprung weight. And some of those items would be, well, number one, the biggest one would be the wheel and tire assembly. Because when you hit the railroad tracks, this whole corner will go boom, boom, like that. So wheel assembly, big unsprung weight deal. Next, we would have everything that moves in the suspension when you hit a bump. Everything that goes up and down, which would be rotor, spindle, control arms, even the shock and spring assembly, as well as the tie rod, which isn't on here. That whole system is all unsprung weight. Now in a race car, we want the suspension to be very responsive when we do hit those little bumps in the racetrack. And the lighter we can make that unsprung weight, the more beneficial it is. There is a statistic, they say a bunch of different things, the authorities on it, but it's in the order of 4 to 1, the benefit, the weight benefit of unsprung weight to sprung weight. Let me explain a little bit. For every pound of weight that you take off your tire, it's the equivalent of taking 3 to 4 pounds out of the center of the car, meaning that the value of a pound is much greater when you're talking unsprung weight than sprung weight. Again, for every pound you could remove of unsprung weight, whether it be from the rotor or the tire, it'd be the equivalent of making your car 3 to 4 pounds lighter on the sprung weight. The next item under front end geometry is the concept of Ackerman. What Ackerman is, it's the concept when you, for example, turn into a parking lot and you're turning real sharp. If you were turning to the left, for example, the left front tire travels a shorter path but a sharper arc. So the left front tire would have to turn farther than the right front tire. Let me show you with a little example. This would be the path that a race car would follow around a racetrack. You can see I have two different radiuses drawn here. One which would be similar to the path that the left side wheels would follow. The other, big R, being the path that the right side wheels would follow. And you can see once you get up in the center of the corner that the left front wheel actually has to turn farther than the right front wheel because it's turning a sharper corner than the right front wheel. And the amount of difference when you turn the wheel, the amount of difference between the left front and the right front wheel, we refer to as Ackerman. And how you find Ackerman is exactly what I've done here. Basically find the radius of the racetrack or the turn that the car is going to travel through. Draw a dotted line, I don't know if you can see it or not, through the rear axle assembly to the center of the corner, the radius of the corner, and do the same with the front wheels. And that will dictate the angle that the left front wheel needs to be at relative to the right front wheel in order to negotiate the corner. In general, when racing on tracks of a half mile or less, there's some guidelines that we look for in the car in terms of Ackerman. We use a set of items called turntables, which are nothing more than a couple of turn plates that you would put under the front tires so that when you turn the front wheels, sitting still, turn the front wheels, it would tell you how many degrees each wheel turned. Now, if you take any of our Dwarf cars and put turntables under the front wheels and turn the right front wheel 10 degrees to the left, we're looking for anywhere from 11.5 to as much as 13 degrees of travel on the left front wheel. So in other words, if the right front wheel turns 10 degrees, we're looking for at least 11.5 degrees on the left front wheel. And that's indicative of how much Ackerman is in the car. In general, once the car is constructed, there's not a whole lot you can do to change the Ackerman. About the only thing you can do is make sure that the spindles are the best that they can be. Our spindles are all designed such that the steering arms are pointed parallel with the chassis. In other words, this being the front spindle, this being the front view of the front suspension, this being the front spindle, our steering arms would lie right here so that the front view would show that the steering arms are parallel to the chassis. The top view would look something like this. If this was the frame rail of the car, our steering arms, this would be the wheel center line, our steering arms would run straight ahead, just like that. and then our tie rods, our steering rack, like that. And the way that setup is, when you do turn the car to the left, again, if you turn the right front wheel 10 degrees, you're looking for at least 11.5 degrees on the left front. That's Ackerman. If you put your car on turntables and do that little check, it'll tell you if you're in the ballpark or not. The next concept is that of bump steer. What is bump steer, you might ask? Bump steer is an occurrence that takes place when the front suspension travels up and down and the tires tow in and out. That towing in and out of the tires as the suspension travels up and down is what's called bump steer. For example, here would be a top view of a tire. This would be if you were in an airplane looking down on a tire, like on an open wheel car, for example. As that car is going even down the straightaway and it's traveling up and down, the tire's traveling up and down, the wheel will be towing in and out just a little bit. So in other words, as the racer's going down the track and the tires are traveling up and down, the amount that they tow in and out due to hitting the bumps is called bump steer. In racing, bump steer is an undesirable characteristic to have in a car. Number one, you need to know how to check for bump steer, and number two, you need to know how to correct the bump steer. In order to check for bump steer, there are commercially available bump steer gauges, and it is possible to make your own. A bump steer gauge is nothing more than a pair of dial indicators that mount on a fixture. A fixture such as a flat bar, bolts or mounts on the side of the wheel or tire like this, and then there's a couple of dial indicators that touch the plate. And if you remove the springs and the shocks from the car, you can manually travel the suspension up and down. And as you travel them up and down and the tire tows in and out, it will register on these gauges. Again, you want to minimize the amount of bump steer that your car has. Bump steer is not a good thing. Bump steer is the item that makes your car feel darty when you hit a bump and your car feels like it darts to one side or the other or has an unstable feel about it. Bump steer is the major contributor to that. Many Dwarf cars and Legends cars, because of poor design, have terrible, terrible bump steer. I've seen quite a few of them where it makes the car very uncomfortable to drive. Unfortunately, bump steer can be very hard to get rid of. How we get rid of bump steer is once you find out where it's doing what, where it's towing in, where it's towing out, you shim either end of the tie rod on that given wheel until the bump steer is minimized or alleviated. Now, you could shim either the outboard or inboard side depending on whether it was towing in or towing out. Since every car is different, I can't go into detail on each specific car, but I will just say in general, by shimming the tie rods either up or down on either end, you can alleviate in some cases, or at least lessen in most cases, lessen the bump steer. One way to be sure that your car doesn't have a lot of bump steer is to design it or to buy a car that has already been thought out far enough that it doesn't have bump steer. Some of the things to look for in general to alleviate bump steer is, number one, tie rods that run parallel to the lower control arms in the front. Again, this being the front view of the car. If the tie rod was mounted in the same plane as this lower control arm and the same length at the same angle, as the suspension traveled up or down, the lower control arm and the tie rod would be swinging the exact same arcs at the exact same time, and the car would ideally have zero bump steer. Some cars, some Legend cars and Dwarf cars I see have the tie rod running parallel with the upper control arm, which is better than some, but it still is conducive to a lot of bump steer. And about the only way that I know of to alleviate bump steer completely is to have the tie rods parallel to the lower control arms and lying in the same plane and be the same length. And that would be the way to alleviate bump steer. This next section will deal mostly with rear suspension geometry. Rear suspension is almost equally as important as the front suspension. The geometry of the rear has a lot to do even with how the car steers. One of the first topics we'll be getting into is ride height. How to find the correct ride height for the rear end for your car. Again, like the front suspension, the rear ride height is independent of the front. It doesn't matter if it's an inch lower than the front ride height or an inch higher than the front ride height. It's an independent entity in itself. One of the main constraints for determining ride height would be the angle that the lower control arm would lay at. Again, like the front lower control arms, we want them to be flat. Same thing with the rear control arms, or trailing arms as they're called. We want them to be flat, give or take a few degrees. But in general, keep them as flat as you can. That somewhat dictates the ride height of the car. Once you've established the ride height by making the trailing arms flat, the next thing you need to do in order to get good drivability into the car is to find where the instant center is of the rear linkage. In order to do that, all we do is extend the line that runs through the trailing arm and extend the line through the upper link, assuming you have a 3-link suspension, which most Dwarf cars and Legend cars do. And if you extend the line through the upper trailing link, this one intersects right about here. My rule of thumb is that instant center should be no closer to the rear axle than the midpoint of the car. In other words, if this was a 90-inch wheelbase car, this point should be no closer than 45 inches to the axle center line. In general, the farther ahead you make that instant center, the more forgiving the car is to drive. The gentler it'll be on acceleration and deceleration. It'll be much easier to drive. If you're an inexperienced driver, you may want to have it fairly forward. In general though, no closer to the rear end than the midway point of the wheelbase. I like to keep it anywhere from here to even the spindle center line of the front wheels. Anywhere in there, and you'll have a pretty decent drivable car. Another issue we need to talk about is squaring the rear end in the car. We need to make sure that the rear end is pointing in the exact same direction as the frame rails and the front wheels. This is a top view of the Dwarf car's frame, these being the front control arms, this being the rear axle assembly with the wheels. You can see I have this line drawn in here. This is representative of a cross member in the car, which I like to use as a reference point. If your car doesn't have a cross member, the manufacturer hopefully put some kind of tabs marking locations for the rear end. Some means, whether they've drilled a hole or welded a tab, some means of measuring from that tab to the rear axle housing in order to get the rear axle square in the car. Generally, what I like to do is hang a plumb bob over the rear axle assembly. And again, this would be the side view, just like it is in the car here. This would be representative of the axle tube. What I do is take a string with a plumb bob and hang it over the axle and let it hang so that this string is perfectly vertical. And then what I do is go up here to the cross member, which would be right here in this car, and measure straight back from the cross member to that plumb bob on each side. So in other words, we'd hang the plumb bob right here, and we would measure from this cross member straight back to the plumb bob. And we'd do the same thing over here. Hang the plumb bob right here, measure straight back from that cross member to the plumb bob. Now that's assuming the car's never been crashed bad and that cross member is reasonably square in the car. If it's not, you might have some other means like a welded tab on each side or a hole drilled or some kind of a reference point, and that's how you would square the rear end. If you didn't have any of that and you needed to square the rear end and you knew the front was square, what you could do is run a string from the lower control arm ball joint. A lot of times we tie it to like the grease fitting and run the string straight back and over the plumb bob to the plumb bob and measure that distance on each side. And that will also tell you if the rear end is square, provided you know that the front end is square. The next topic on the rear suspension geometry section will be rear axle tracking. And what the tracking is basically the position of the rear end from side to side in the car. The tracking is determined by the panhard bar, which is a lateral locating device, usually mounted to the rear axle here and runs transversely in the car to a frame rail over here. And what that does is it disallows the rear end to move side to side in the car. When you go into the corner, if you didn't have a panhard bar, the body would move relative to the rear axle, or rear axle relative to the body. All it does is a lateral locating device. Anyway, in order to check the tracking of the car, the basic way to do it is to merely measure the distance between the tire or the rim and the frame rail on each side. One big thing though you have to take into consideration, if you have differing wheel offsets, the amount that you measure will differ the amount of the wheel offset. If you have, say, 4-inch offset wheels on both sides, that distance should be equal from the tire to the frame rail, from the tire to the frame rail on each side. If you have a 4-inch tire, 4-inch wheel here and a 5-inch here, this gap right here from the tire to the frame will be 1 inch smaller over here. That's pretty much all there is involved with setting the tracking. Once you do set the tracking, you should check the car again for squaring of the rear end, square the rear end, and just check them each couple times to double check your work. Make sure that the rear end is square and tracking along with the front wheels. There are a couple other ways to check the tracking. You can run a string, wrap a string around the tire and along like this and up to the front tire. Do that on each side and check it that way. Check for parallelism of the tires with the string. The next item we need to discuss is the panhard bar, which I've already touched on, the panhard bar being the lateral locating device. The panhard bar is also a major tuning aid at the racetrack. The panhard bar is also synonymously called a track bar by some people. Some racers, some manufacturers like General Motors, I believe, calls a panhard bar a track bar. In any case, it's the same bar, it does the same job. Rule of thumb for the panhard bar, if I was to draw the rear view of the car, this being the axle assembly, you want to try to keep the panhard bar flat in the car, or as near flat as possible. Panhard bar usually mounts to the rear end on this side and to the frame rail over on this side. Rule of thumb, keep that panhard bar generally as flat as you can. If it has a few degrees, like maybe up to 5 degrees or 7 degrees of angle to it, either way, it doesn't mean that much. Try to keep it flat. What is the most pertinent about the panhard bar is the roll center height. The panhard bar is what determines the rear roll center of the car. And the height of the center of the panhard bar, which is right here, the height that is off the ground, that is the rear roll center height. So, in other words, if the panhard bar wasn't flat in the car and had a little angle to it like this, you would still measure from the center of the panhard bar to the ground to get the roll center height. Now, the roll center height in the rear of the car via the panhard bar is adjustable on most cars. Some of the Phoenix cars I saw, they weren't adjustable, but most of the more recent cars it is adjustable, and it's a big tuning aid. In general, if you can, you should move the whole panhard bar if you have adjustments on both sides. In other words, if you have adjustment on the axle side as well as on the frame side, when you do adjust it, it's best to adjust the whole panhard bar up and down. If you don't have any adjustment, you'll just move the one side and you'll have to live with the angle. Like I say, as long as the angle is less than, I'm going to say, 7 degrees, it's not a real major deal. In general, if you want the car looser or to oversteer more, if the car is too tight, you turn the wheel and the car goes straight, you want to raise the panhard bar. That primarily affects the car coming into the turn and through the middle of the turn. If the car's loose on turn entry and through the middle, the car's chronically loose, you can lower that panhard bar and it will tighten the car up. And usually if you go 1 inch on the bar, move the bar vertically either up or down 1 inch, it's a pretty major adjustment and you should be able to feel it pretty easily. This section is on wheels and tires. Wheels and tires are a very important part of the race car. If you look at anybody that's doing a lot of winning in any division of oval track racing, undoubtedly they not only know a lot about tires, but they are racing with the best tires that they can have. In general, for the Dwarf cars and the Legends cars, there's 2 different types of tires. The radial tires that are the BF Goodrich tires the Legend series runs, and the McNamara or Hoosier bias ply tires that most of the Dwarf car tires run on. In general, the spec tire for the Legends, the BF Goodrich tire, there's not a whole lot you can do with. They don't change in tire pressure, doesn't change the stagger at all. You're very limited. It's a very equal tire for everybody. However, the bias ply tires for the Dwarf cars, there is a lot you can do with them. When you air them up, it changes the size of the tire so you can play with tire stagger. There's just a lot more you can do with them. If you have the opportunity, I would recommend running on the bias ply tires, either the McNamara tires or the Hoosier tires, whatever is permitted. The first major topic we're going to talk about tires is tire stagger. Tire stagger is merely the difference in size between the right side tires and the left side tires. In essence, on an oval track car that turns left, you want the right rear tire to be larger than the left rear tire so that when you get on the throttle, it drives the nose of the car to the left. It keeps the car turning left. Stagger in the front isn't nearly as important. The only thing that's important with stagger in the front is that you keep it consistent. If you have 2 inches this week, try to have 2 inches again next week. If you change the stagger in the front, it changes the cross weight in the car, which we'll be getting into later, and it can upset the handling. The main issue for stagger is in the back. That's where it needs to be watched, and watched religiously. As I said earlier, the radial tires, they don't change with air pressure. The stagger doesn't change at all. They're pretty much the same size whether they have 30 pounds in them or 50 pounds. Whereas the bias ply tires, like the McNamara tires or the Hoosier tires, they change dramatically with tire pressure. In order to obtain tire stagger, we frequently will let the left rear tire down sometimes as low as 10 pounds in order to get the amount of tire stagger that's desired to get around the racetrack. Which brings into mind tire pressures. Well, being that Dwarf cars are relatively light, we find a ballpark range for tire pressures, for the bias ply tires mind you, to be approximately 25 pounds right side, left side 18 to 20 pounds, with the exception of the left rear. The left rear should generally be whatever you need to make it to get that amount of tire stagger. We don't recommend going below 10 or 8 at the very lowest, 8 pounds in the left rear. But that change of tire pressure is what gives you the tire stagger. In general, for most tracks, quarter mile to half mile, in general we run 2 inches of stagger in the back. We will change it a little bit if it's a real tight corner, or decrease it a little bit if they're long sweeping corners like on a half mile track. But in general, 2 inches. If you want, you can run 2 inches in the front too, just for simplicity, and that way if someone punctures a left rear tire, for example, you can take your left front and put it on the left rear and play with your tires that way. It almost gives you an extra set of tires to play with. When you do change the front tire stagger, it doesn't affect the car nearly as dramatically as it does in the rear. So try to keep your rear stagger consistent all the time. Pretty much every time our car comes out and comes back in, we measure tire stagger and tire pressure. We keep really good records on it so that we always know where we're at. When a problem arises, the first thing we look at is the tires. Speaking of tire stagger, there's several different ways to measure your tires for tire stagger. First off is the old traditional way, which is using a real thin tape measure. And basically what you would do is jack the car up and run the tape real carefully around the center, around the circumference of the tire. In the center, pull it tight like you were measuring someone's waist, and record the number. You do that to each side and then subtract the difference, and for like our application, you would end up with 2 inches. There is another way. It's much quicker at the racetrack. It's not quite as accurate, but it's very quick, and that is to use a stagger gauge. Here I have a commercially available stagger gauge. I believe they're relatively inexpensive, in the $50 range. They're a very convenient item to use. All you have to do to use the tire stagger gauge is put it on the center of the tire and just fish it up and down and take the highest reading. This one is 74 1/4 inches. It makes checking tire stagger very simple. Speaking of tire temperatures, I have here a digital tire pyrometer. And what this instrument is used for is when the race car comes in off the track hot, one of the crew members will immediately go up to each and every tire and take 3 temperatures across the tire. First the outside, and record it, then the center, and then the inside. Those 3 numbers will be recorded. He'll walk around the car and do all 4 tires, and that'll not only be kept in records, but a few minutes later will be analyzed to determine if there's a handling problem or if there's any trouble at all, what can be improved with the tires to make the car go faster. Once the tire temperatures are taken and recorded, they need to be analyzed. Let's take a look at some tire temperatures that we recorded off a race car when it came in. Right front tire showed 140 degrees on the inside, 110 in the center, and 130 on the outside. Being that the inside tire temperature on the right front tire was so low, it's indicative that the tire had too little air in it or was underinflated, causing the tire to ride more on the sidewalls and generating heat on the sidewalls rather than in the center. Looking at the right rear tire, this tire came in, was 120 degrees on the inside, 160 degrees in the middle, and 115 degrees on the outside. Again, we've got a big temperature difference where the center of the tire this time is much higher than either side, much hotter, which is indicative of an overinflated tire. The tire had too much air in it, and it caused it to ride mostly in the center of the tire and heat up the center of the tire. Those are the two major ways that you can tell an underinflated tire or an overinflated tire. There's also other things you can tell by taking your tire temperatures. For example, if the camber in the right front of the car is correct. Let's take a look at this race car when it came in. Let's look at the left front. Left front tire on the outside 160, middle 140, inside 120. Well, this tire was substantially hotter on the left side of the tire than it was on the right side, which is indicative of too much positive camber. In other words, that left front wheel was out too far at the top, and when the car was going down the straightaway, it was actually riding on the left sidewall somewhat, generating tire heat. Let's take a look at the other example here, which was the right front of that car. That one came in 150 degrees on the inside, 160 in the middle, 160 on the outside. Being that this temperature is 10 degrees cooler than this temperature, it's indicative that the camber was too far positive or too straight up. What needs to be done is the camber needs to be increased or tilted in until this temperature on the inside exceeds this outside temperature by 5 to 10 degrees on a dwarf car. In general, all 4 of your tires, especially the front tires, this number all the way to the left, which would be towards the infield, should be 5 to 10 degrees higher than this number on the right, and the center number falls somewhere in between. So an ideal tire temperature, for example, would be 155, 151, 149. That would be an ideal tire temperature, where it's an even distribution across, higher temperature on the infield side than on the outside or inside, however you want to view it. Grandstand side, infield side. Let's take a look at another example here. Here what we're doing is just looking at the overall temperature of the tires. You can see the distribution, 145, 141, 138. Looks good. That's a good distribution. Likewise, on the right rear tire, 165, 160, 159. That's also a good distribution. The thing to notice here that in general, these 3 temperatures, which are around 160, 162 degrees on the average, are substantially hotter than these, which are 142, 143 on the average. This indicates that the right rear tire was doing an excessive amount of work and that the car was in an oversteer or loose condition. On the next example, we've got tire temperatures on the right front of 164, 159, and 138. On the right rear, we have 147, 142, and 138. In this situation, you can see that the right rear tire is substantially cooler than the right front tire, which indicates the right front tire was really working hard and that the car was probably understeering or pushing. Went into the corner, turned the wheel to the left, the car really wanted to go straight. Generated a lot of heat in the right front tire. In addition, there's another thing I need to mention, and that is that if you look at the tire temps, whether they're a front tire or a rear tire, the temperature distribution is always that the left side of the car, or the infield side of the tire, I should say, is hotter than the grandstand side of the tire. In the rear, it's because of tire stagger. The tire stagger making the tires run more on their left sidewall, each one of them. And in the front, it's because of the camber. Positive camber in the left front makes the left front tire run on the left sidewall down the straightaway. Negative camber in the right front makes the right front tire run on the left sidewall down the straightaway. In all four situations, you will see that the temperature on the left side of each tire is a little bit higher than the temperature on the right side. This next portion concerns wheels. Wheels, again, with the tires, very important part of the race car, and you do have a couple different ways you can go with wheels. One of the major things is that the wheels you use are often restricted by the rules, or if the wheel itself isn't, the width that it might make the car would be. Let me give you an example. If you have a restriction on track width of, let's say, 60 inches, you can't put super wide wheels on your car because your car will be too wide then and against the rules. But where permitting, I'd encourage to run the deepest offset wheels that you could within reason, provided that the rules allow them and that your car meets the track width requirement if you have one. Also, if your track doesn't specify a certain width rule, in general, you should try to run the widest wheel that you can. Most tracks, most dwarf car tracks, run 7 and 8 inch wheels. Also, in addition to the size of the wheels, the weight of the wheel is very important. It's always best to have the lightest wheels for two reasons. Number one, it reduces the unsprung weight that we talked about earlier. And number two, in the event of a collision, the wheel will deform and it will save a lot of suspension components. We've been into the wall before pretty hard, and a ductile wheel, a soft, lightweight ductile wheel, will deform and absorb a lot of the energy and keep from wiping out a lot of suspension components. Here are a couple wheels. We're going to measure them real quick for back spacing, just so you know how to do it. All you do is, having the wheel, the tire dismounted from the wheel, lay the wheel down flat on the floor and stick the tape measure in there and measure to the back side, like the surface that the rotor would be touching. This one comes up 4 inches right on the head. So that's a 4-inch back spacing wheel. Once you do have your wheels measured, you should write on them what the back spacing is. That way you'll always know. They're very hard to measure with a tire on there, so now is the time to do it. We'll measure this wheel real quick, and this one comes up 3 inches on the back spacing. It'd be a good idea if the rules allowed to run the 3-inch wheels on the right side and the 4-inch wheels on the left side. That would increase the left side weight a little bit, and provided that the car was still narrow enough to meet the track width requirements, you'd be all set. There's no real magic to springs and shocks. We've seen just about every spring and shock combination set fast time at just about every track we've been to. There's no real magic behind it. The only thing there is a little bit of common sense. The first thing to remember about springs are the primary function of the springs are to support the car. The springs control the compression as the car hits a bump or rolls, and the shock's job is to control the spring on rebound. So if the car was rolling and the tire fell in a pothole, it's actually the shock's job to damp the motion so that that spring doesn't just blast into that pothole. Some of the things to watch when dealing with the springs and shocks. Number one, you need to watch the travel of your shocks, because the travel of the shock is indicative of the travel of the spring. Most shock assemblies that you buy, the Dwarf cars primarily using coilover type shocks, have a little rubber grommet that you can slide on the piston rod, and if you slide that all the way down before the car goes out, when it comes back in, by looking at that grommet and how far it's traveled from the body of the shock, you can get some idea of what kind of travel you have in all four corners. Another major consideration on springs and shocks is the motion ratio of the suspension. Sounds like a big term, but it's really not that complicated. All the motion ratio is, it's a ratio of the position that the shock is mounted in, and when I say shock, I mean shock and spring assembly, versus the position of the ball joint, both of them with respect to the inner pivot. This being the lower control arm, this being the inner pivot. All the motion ratio is a fraction. It's this distance from the shock to the inner pivot divided by the distance from the ball joint to the inner pivot. What this motion ratio does, it's a correction factor for the spring. Because the spring's not mounted out at the ball joint, the spring has more wheel force working against it, and just because of that, the shock spring assembly doesn't work as effectively. For example, if this shock and spring assembly was mounted over here, it would have way less force against the tire than if it was mounted over here. And just a brief correction factor for that, I've got an example on the board. The distance from the shock to the inner pivot being small l, the distance from the ball joint to the inner pivot being capital L. We're going to measure this. This came out to about 5 inches. Big L came out to about 9 inches. If we were going to put a 200-pound spring in this car and we wanted to know exactly how the motion ratio affected this spring or shock, because it affects them both the same, what we'd do is we'd take our 200-pound spring and multiply it by the motion ratio, which is L, small l over capital L. So 200-pound spring times 5 over 9, which is small l over capital L, ends up being only 111 pounds. So even though you put a 200-pound spring in your car, the car actually only sees it as a 111-pound spring because of the motion ratio. And the main point that I'm trying to make here is that a 200-pound spring in one car isn't necessarily going to perform as a 200-pound spring in your car, because the motion ratios aren't necessarily the same. Some cars may have this spring and shock assembly mounted much closer to the ball joint. Some may have it mounted a little bit closer to the inner pivot. Ideally, if the shock was mounted at the ball joint, this 200-pound spring would truly be a 200-pound spring to the car. The only exception is the angle of the shock, and when I say shock, I mean shock and spring assembly, the angle that deviates from vertical also lessens the effectiveness of the shock. As this shock is tilted in different positions, such as if it was tilted in this position here, it would be much less effective against the wheel tire assembly than if it was in this position or even vertically. So therefore, a spring isn't ordinarily a spring, and if you've got a racer friend that thinks he's got the hot setup for springs, they might not necessarily work in your car. Once we get a set of springs and shocks that work real well in the car, we generally don't change them very often. There's only a few times that we would even consider changing springs. One of them would be if the banking substantially increased on a track that we went to. For example, we went to a track, we had never been there before, and we suddenly find out that the banks are huge. I mean, you know, 30 degrees or more, 35 degrees, and we're used to running on a 20-degree bank or even less. Then we might consider changing the springs only to keep the car from bottoming. Again, we would push our shock grommets down on all four shocks, go out and make a few laps with our existing springs, and if the car is coming close to or is bottoming out, then we would consider changing springs. The only other time you should really change springs once you get a good setup, and that is being that you're running on quarter miles, 3/8 and half miles. You're running on the same size tracks all the time. The only other time you would change a spring is if you develop just a chronic problem that you could not alleviate, being it oversteer or understeer. In general, whenever you increase the spring rate on an end of your race car, it will decrease the performance in relative terms. Likewise, whenever you soften the springs on either end of your race car, it will increase the performance of that end of the race car in relative terms. For example, if your car is plagued with a chronic understeer problem all the time, by going to softer front springs or stiffer rear springs, it will help balance the car and make the car turn better. Likewise, you could have a car that has a chronic oversteer or chronic loose condition, and you would remedy that by either softening the rear springs, stiffening the front springs, or both. Generally, whatever end of the car you increase the springs on, it will decrease the performance, and whichever end you decrease the spring rate will increase the performance. Kind of confusing. We don't normally do it unless there's a chronic condition that we just can't avoid. The other thing you need to be watching for is in the case of bottoming out. If your car is bottoming out, you need to look at why it's bottoming out. Is it bottoming out solely because it's hitting one big bump in the racetrack and bottoming out, or is it actually bottoming out for a moment in time, a few moments in time through the corner? Is it bottoming out because of a load or because of an impulse? If it's bottoming because of an impulse, such as a bump, you need to increase the shock rate. If it's bottoming because of a load, because of rolling into the corner too hard, you need to increase the spring rate. I'm going to give you a few starting points for spring rates and shocks for the Dwarf cars. This is what we found has worked very well. In general, for the front of the cars, being that there's no sway bar, which many cars don't have, we spring the cars anywhere from 200 pounds per inch to 250 pounds per inch. Keep the springs in the front somewhat even. You don't need a large spring split. You don't need to have a 250 in one corner and a 150 in the other. Keep them close. A lot of times we'll spring the cars dead even in the front. Likewise, if you have a car with a sway bar, equipped with a sway bar, it doesn't need as much roll couple from the springs, and the spring rates can actually be dropped somewhat. For most cars that utilize a front stabilizer bar, or sway bar as they're called, we recommend springs in the 160 to 200 pound range. And again, keep the spring rates similar on each side. Don't put a big spring split in there. You don't need a 225 and a 125 or a 160 or anything like that. Keep them fairly close. You'll find the car performs better that way. In the rear, the approximate spring rate might change a little bit more. We've seen them run as light as 80 pounds and as stiff as 150 pounds and work real well. That's kind of a big range. Most of the cars, we like to spring them in the 100, maybe 125 pound range, and again, we try to keep them even. We don't go for a real big split in the car. It doesn't seem to work real well. You can split the springs in the rear if you're having a handling problem. For example, a chronically loose car, you may want to put a heavier left rear spring in than right rear spring, and that will help tighten the car up. Again, we usually don't change springs except for when the banking increases or decreases drastically at a racetrack, when we have a chronic understeer or chronic oversteer condition. Those are really the only times we change shocks once we get a set of shocks and springs that really work good. Our recommendations for shock absorbers, there aren't a whole lot available for Dwarf cars. We generally run racing shocks that are 50-50. Of course, they are coilover shocks, much like this one right here. This is a Pro shock. This would be a rear shock for us. The last digit in the part number usually indicates how stiff the damping is on the shock. This is a 62, model number 62, which I believe means 6-inch stroke on the shock, and the corresponding number for the damping coefficient, or how stiff the shock is a 2. Generally, we run 2s on the back and 4s on the front. Now that number stays the same whether you have a Carrera or just about any make shock. It's a relative number. A 2 is softer than a 4. Shocks are available all the way up to, I believe, number 8, which is extremely stiff, really doesn't have any place in Dwarf car racing. And I believe the lightest that I know of anyway is the 2, and the 2 is a good shock for the back, and again, the 4 is a good shock for the front. Both shocks are racing shocks, and they are 50-50 shocks. Okay, this topic discusses weight and balance. There's 4 major things that we need to know and that we need to talk about concerned with weight and balance or scaling of the car. If you're familiar, the cars are frequently put either on racing scales or grain scales at all four corners, like this one is, and the cars are weighed. All four corner weights are taken, and there's some computations made. Generally, there's four things that we need to know. One, the total weight of the car, which generally is determined by your rules. The cars are usually weighed on the scales here with the driver in and fuel load. Secondly, we need to know the front percent, which would be whatever the percent is in the front. It would basically be the front wheel weights divided by the rear wheel weights times 100. The left side weight, which would be the sum of the left side wheel weights divided by the total weight of the car times 100. And fourth would be the cross weight. There's a lot of slangs for that, and we really need to spend some time defining it. Some of the other terms for cross weight that are interchangeable: diagonal, wedge, or sometimes even bite. Let's take a few minutes and we'll talk about cross weight. What is cross weight? How do you get it? What good does it do? All cross weight is the sum of the right front tire weight plus the left rear tire weight divided by the total weight, and then times 100, and we times 100 in order to put it into a percent. What the cross weight does for us is it tightens up the back end of the car. Okay? If we put extra cross weight in the car, expressed as a percentage, the car will be tighter. The back end will not be loose. It'll be more conducive to understeer. We always express cross as a percent. Generally, when we're on the scales, and we're going to talk a little bit about scaling it now. Well, before we even get to the scales, there's a number of things that we have to do to the car to have it ready to go on the scales. Number one, of course, we have to have a level floor and have the scales level. If you have scales and they're racing scales, the manufacturer will have detailed instructions on how to set your scales up. As far as the car, setting it up to scale it, number one, if it's equipped with a stabilizer bar, that should be neutral. You should either disconnect it or just have it neutral. Secondly, the car needs to be race ready, needs to be full of fuel, needs to be full of oil, needs to have a driver inside with helmet on, everything. You need to simulate race conditions, basically. Also, the car needs to be set, the ride heights need to be set on all four corners. And of course, as we talked about earlier, the geometry of the rear suspension and the geometry of the front suspension will determine what ride heights work the best. In addition to having the ride heights correct, the front end alignment needs to be completed on the car, and also the tire pressures need to be at whatever pressure you would race the car at. Once all this is done, the car is ready for the scales. One of the major things to remember when you're on the scales is that provided you don't move any weight on the car and that you only play with the load bolts or coilovers, there's certain things that happen and that don't happen. The things that don't happen I'll go over first. As long as you don't add or move any physical weight in the car, the total weight of the car will always stay the same. The front percent or rear percent will always stay the same. The left side percent will always stay the same. The only thing that changes when you have your car on the scales and you play with the load bolts is the cross weight. And again, the cross weight is the sum of the right front and left rear relative to the total weight of the car. If you have a real high cross weight number, for example, if we turn the load bolts in such a way to increase the cross weight way up, 60–65%, what ends up happening is the right front tire is very, very heavily loaded, and so is the left front tire. The right rear tire is fairly light, and the left front tire is fairly light. And when the car is actually going around the track and the weight transfers to the right side, the left front tire is hardly doing any work at all. These cars really do work the best at about 50% cross weight. Of course, this depends on a lot of things: how much power you have, how much stagger you have, a lot of other things. But in general, a good starting point is 50% cross weight. We still need to talk about cross weight a little more. It's really a difficult concept to get across, but we'll talk about it. In order to increase cross weight, you can do many things. What we do is if we adjust a corner on the car, for example, if we turn down the load bolt on the left rear corner of the car, it will compress the spring and it will raise this corner of the car. Simultaneously, it'll compress the right front spring and load that corner of the car. Simultaneously, it will unload the left front and unload the right rear. So when you make an adjustment on any corner of the car, if you make an adjustment, it affects all four corners. So again, if we turn down the load bolt on the left rear, it compresses that spring, which raises this corner of the car, which dips the right front and compresses that spring. So we just loaded those two tires, increased the load. And of course, because the total weight stays the same, we must have just lightened the left front and right rear, which we did. What does this all mean? Well, number one, when you do change a load bolt or jack screw, however you want to call it, coilover, you need to change all four corners and do it all evenly. But you don't do them all in the same direction. If you wanted to put a little bit of wedge in, like say 1%, what you would start out with doing is putting 1/4 turn in on this corner, put 1/4 turn in on that corner, and when I say in, I mean clockwise or tightening up the spring. You would take 1/4 turn out of the right rear and take 1/4 turn out of the left front. Then you would have moved each corner 1/4 of a turn, you would have kept the ride height the same, and you would have increased the wedge in the car by about 1%. It takes a little while to think about it and really get used to it. But again, when you're on the scales and you're turning the load bolts, the only thing that you're changing is the cross weight, diagonal, wedge, bite, whatever you want to call it. Everything else will stay the same. As long as you don't physically move weight around the car, everything else stays the same. Cross is both a good thing and a bad thing. If you have a car that's loose and you put cross weight in it, it will tighten it up. But it tightens it up at the expense of the steering. If you go too much cross weight, keep increasing it, and it gets to be too much, the car will not steer anymore. When you get on the gas, the car will go straight because the rear end will have so much traction and the left rear wheel will be loaded so heavily that it will drive the nose of the car to the right. Consequently, if you have too little cross, the car will be loose. The car will have much more traction at the right rear wheel than it will the left rear wheel. And also the front end will steer so good that when you get on the gas, the right rear wheel will drive the nose of the car to the left and the front will steer so good it'll want to go to the left real easy anyway, and the car will end up being loose. Again, these cars work the best about 50% cross weight. Once you find a good setup for your car where you're going real fast at your racetrack, it is a good idea to take the car home, put it on the scales, record those numbers, and keep good track of them. You need to really keep good records when scaling the car. Scale the car in the same place every time. That way, if you mark the spots, for example, on your garage floor, the scales will be in the same position every time, and you'll get a lot better repeatability and a lot better results. Here are some basic guidelines as far as numbers setting up your car for competition. Total weight is going to be dictated pretty much by the rules, whatever your track is. So that one doesn't matter so much. In general, for dwarf cars, I'm going to say it's going to be around 1,200 pounds. Keep the car as light as possible. Don't run it heavier than you need to. Extra weight does not make for a faster car. Your car will always be faster when it's lighter, even though you might have to work with it a little bit more. Secondly, pretty straightforward. Front percentage, rear percentage. Very even. 50%. 50% front, 50% rear. That's to say the sum of the weights of the front tires would be equal to the sum of the weights of the back tires. Plus or minus 0.5% or even 1%. No big deal. Left side weight. Left side weight, keep it as high as you can. Whatever you can do to increase the left side weight within the rules, you'll increase the performance of the car. Most dwarf cars we find come in right around 52% only. Whatever you can do within the rules to increase the left side percent without adding excessive weight, it's a good thing to do. And the last and probably the most important thing is the cross weight. A good place to start with a dwarf car is 50%. We've seen them work everywhere from 46% all the way up to 58%, depending on what the stagger is, what the driver prefers, how well the car is set up. 50% is a good starting point. If you follow these numbers and follow the scaling directions, you should have a pretty fast car. Chassis handling is the key to winning races. We're going to be talking about three things primarily when we're at the racetrack: oversteer, understeer, and neutral steer. There's basically only four things that we try to do at the racetrack in order to cure a handling problem. One of them is adjust the tire stagger. Secondly, adjust the wedge or crossweight in the car. Third, adjust the amount of rear brake or the brake bias. And fourth, move the rear roll center via moving the panhard bar up or down. One of the important things when you're tuning the car at the track is to get a good feel for what the car is doing and where it's doing it. For example, if the car is understeering coming into the corner but loose coming off, what we would do is address the problem of understeering coming into the corner first. That problem sometimes complicates the latter problem. So pay close attention where on the track the car is having a problem and address the first problem first. That is, if it's pushing first and then getting loose, address the push first. And a lot of times you'll see that the loose condition will alleviate itself. When we're at the track, we need to always pay real close attention to keep the car balanced, keep it in neutral steer. Even if it's a minor push or a minor loose, understeer, oversteer, we need to be on top of it and make minor adjustments to alleviate it. There are several types of understeering or pushing conditions. One is a brake push coming into the corner, perhaps too much front brakes. Another one is not being able to turn or pushing in the center of the corner, possibly from too much crossweight. A third type of push or understeer is what I call, it's slang, a power push. And that is when you pick up the throttle and the front wheels just won't turn the car anymore. The car wants to go towards the wall. There is another kind of push that's a push induced by having something binding or geometrically incorrect. If you're on top of your car, you'll be able to catch that one by watching the wheel travel and sometimes even pulling the springs out and traveling the suspension. Make sure nothing's binding. In order to address the problems of understeering at the racetrack, and this is pretty much in order, the series of steps you would take to alleviate. Number one, if it was pushing coming into the corner, you would increase the rear brake. By increasing the rear brake, it would free up the back end a little bit and make the car turn in better. You'd also be able to stop a little bit better, and the car would turn when you get to the middle. Secondly, would increase tire stagger. Although tire stagger helps us get off the corner by driving the nose of the car to the left, it also helps loosen the car up or free the car up a little bit coming into the corner. Decreasing the wedge will also make the car steer into the corner a little bit easier. Raising the rear roll center height via raising the panhard bar will loosen the car up coming into the corner. I don't recommend doing this until you've tried everything else, but if you decrease the front spring rate, most times it will help the car steer into the corner or alleviate a push. At the same time, you could increase the rear spring rate, which would also help loosen the car up coming in, but it would also take away from the overall speed of the car. The last two that I mentioned, in decreasing the front spring rate or increasing the rear spring rate, I wouldn't recommend unless you've done everything else first. If you're having a problem with the car understeering coming off the corner, in other words, the power push type situation, the number one thing to do would be to increase the rear tire stagger. What that will do, being that the right rear tire will be bigger, it will drive the nose of the car to the left, and it'll help alleviate the push. If you try that and it doesn't alleviate the push, or not as much as you wanted it to, you can decrease the cross weight or the wedge in the car, but keep in mind that it'll also loosen the car up coming in. Again, in a last-ditch effort to remedy the situation, if you decreased the front spring rate, it would help alleviate the push off the corner. I don't recommend doing it until you've tried everything else. And again, always be checking your car to make sure that there's nothing binding or geometrically incorrect on the front steering. The next aspect we're going to talk about is oversteering or loose conditions. And again, you always need to pay attention, where on the track is the car getting loose? Is it getting loose coming in? Is it getting loose in the middle? Is it getting loose coming off? Is it getting loose because of too much rear brake? Is it getting loose in the middle because of lack of cross weight? Is it getting loose off the corner because of lack of cross weight? In other words, a power oversteer or a power loose condition. If your car is loose, there's a number of things you can do at the track to remedy it, and these would be the ones I would try, probably in this order. Number one, if it's loose coming in the corner, decrease the rear brake or increase the front brake. Number two, if it's loose getting in the corner, you can lower the panhard bar, which will lower the rear roll center and also tighten the car up coming into the corner. You can increase the wedge in the car, but remember, if you increase the wedge in order to get the car in to the corner without getting loose, it may have a tendency to push getting off the corner. Likewise, if you decrease the stagger coming into the corner, it will tighten the car up coming in, but it will also tighten the car up coming off the corner. If you're having a problem with the car being loose coming in, it could be that you need to adjust the rear suspension instant center that we talked about earlier. And of course, we do this by adjusting the upper control arm or upper trailing arm on the rear suspension. What you would want to do is move the point of intersection, the instant center, towards the front of the car more, and that will alleviate a loose condition or help alleviate a loose condition coming into the corner. If your car is equipped with a front stabilizer bar, check the bar. Make sure that it's not loose or preloaded in the wrong direction. We don't recommend preloading the bars very heavily at all for oval track use. If your car is having a bad problem being loose into the corner, also make sure, go through the geometric things, make sure the rear end is square in the car. A rear end that's out of square will tend to be loose coming into the corner. And again, as a last ditch effort would be changing spring rates. Decreasing the rear spring rate, making the rear springs softer would help the situation, or making the front springs stiffer. Again, that's kind of like a last-ditch effort to remedy the situation. In order to remedy a oversteer or loose condition coming off of the corner, there's a number of things you can do. Number one would be to decrease the tire stagger. Decreasing the tire stagger will tighten up the back end, primarily off the corner when you pick up the throttle. Secondly, you can increase the wedge or increase the cross weight of the car. Increasing the cross weight will do two things. It'll increase the load on the left front tire, which will tighten up the car, and it'll also increase the load on the right front tire, which will give the car a little more of a tendency to push. Increasing the wedge on a car loose leaving the corner can help remedy the problem. Third thing that we haven't really touched on too much yet is shortening the rear suspension instant center. Just like when the car was loose, we lengthened the rear suspension instant center. If the car is loose leaving the corner, we need to shorten the rear suspension instant center. And we would do that again by adjusting the upper trailing arm. And we would actually move the upper trailing arm, the forward pivot point would go down as to make the instant center closer to the center line of the car. Also, we need to check the bar. Make sure that the bar is not preloaded. That is a sway bar or stabilizer bar. Make sure the bar is not preloaded the wrong way, if so equipped. Most of these cars, or many of these cars, don't have the front stabilizer bar. And also, a minor effective thing to do would be to lower the panhard bar, or the track bar as it's called, in the rear of the car. Lower it a little bit, like maybe an inch at a time, ½ inch to an inch at a time, and that would help tighten the car up. But it'll help tighten the car up all the way around, not just off the corner. That's pretty much in a nutshell some of the adjustments you can do at the racetrack to help tune your car in. And again, remember, there's basically only 4 things that you do at the racetrack. You really don't have time to reinvent the wheel, and they are: adjust the tire stagger, increase the tire stagger if the car is too tight or too pushy, decrease the tire stagger if the car is too loose or oversteering. Same thing with wedge. If the car is too loose, increase the wedge. If the car is too tight, decrease the wedge. And I use the terms wedge and cross weight synonymously. Also, the panhard bar. If the car is too loose lower the panhard bar. If the car is too tight or pushy, raise the panhard bar. And one of the biggest things I can advise is when you're racing the car, the only real adjustment you have while racing is the rear brake. If you have a rear brake adjuster that's accessible in your car somewhere, whether it be foot operated or hand operated, and your rules permit, having a rear brake bias in your car is the only adjustment you can ever make during racing, and it turns out to be a very good adjustment that will help you perform much better on the racetrack and possibly even win races. Here's some miscellaneous tips that'll help you win races. Of course, we know the chassis is the key to winning races. Most of the races that you win are going to be because of hard work. In fact, the number of races that you will win will be proportional to how hard you work. Keep good records. There's no substitute for good records. Make a long safety checklist and execute it weekly. Safety is very important. The last thing you want to do is get hurt in a race car. Perform safety items before you need to use them. When you're racing and at the track, use the best tires available. Don't try to win on cut-rate tires. It won't work. Use the best tires. Who's ever going the fastest has the best tires. A lot of times on the Dwarf cars, when you're taking your tire temperatures, you might have a hard time because the Dwarf cars don't always generate a whole lot of heat in the tires. It takes a considerable amount of laps, probably 20 laps in a Dwarf car, to generate any appreciable amount of heat for you to measure. Keep the rear end of the car square and tracking straight. When you're scaling the car, add or move lead weight as necessary to obtain the desired percentages. Keep the car balanced at all times. This means no oversteer, no understeer. Keep it neutral steering as best of your ability. Carefully watch things like tire stagger and tire pressure. When you're at the racetrack, there's basically only 4 things that you're going to need to tune the car. Changes in tire stagger, changes in cross weight, changes in brake bias or brake proportion, and panhard bar height, which is rear roll center height. Those are basically the only 4 things you're going to be using at the racetrack. When building a car, keep the unsprung weight as light as possible. That means wheels, tires, rotors, anything that goes up and down when you hit a bump. Keep it as light as possible. The benefit is 3 or 4 to 1. Also, when building a car, remember what I call the 3 L's. Keep the components, keep them low, keep them to the left, and keep them light. Check weekly for things like loose bolts, bottoming components in the suspension, or anything that could be binding. When you're at the racetrack and you're actually in the race, about the only tuning aid you have is that rear brake adjuster. Get a rear brake adjuster in your car, provided the rules permit it, and use it while racing. It's the only tuning aid that you truly have while you're racing. Now that we've covered all the key aspects in Dwarf car, Legends car, chassis setup, I'd like to thank you for watching this presentation. I'd also like to thank the fine folks at JackSports Small Time Racing for providing this facility and these fine Dwarf cars to do the presentation with. If there's anything I covered too quickly in the video, just hit your rewind button and view the tape again. I'm sure you'll find that you'll race safer and faster. Follow the chassis setup instructions, and I'm sure you'll find it much easier to win races. I'm Tristan Dupuy, and we'll see you in the winner's circle.